Hello, this is Steve KT Math, and in this video we're gonna solve this double integral. So let I be equal to this integral, the integral from 0 to 1 and integral from 0 to 1 of square root of x squared plus y squared dx dy. And here you can see that we have the x squared plus y squared, we have x squared plus y squared here. So it should be like simpler, it should be more convenient to change it to the polar coordinate. And so let's change this to the polar coordinate. So x squared plus y squared is r squared, and square root of r squared is r. Alright, and dx dy is equal to r d theta. r d theta. And so the integrand, square root of x squared plus y squared times dx dy is equal to r squared d theta, because we have r times r here, so that's r squared. And now for the boundary, for the bound of theta and r, well, so theta will go from 0 to pi over 2, because so here the region we're integrating over is a unit square. The region we're integrating over is a unit square because x goes from 0 to 1, y, same for y also goes from 0 to 1. So we're integrating over a unit square, and so the theta, which is the angle, like the angle starting from the x-axis, the positive x-axis, is, well, the theta will go from 0 to pi over 2. That should be pretty straightforward. It's just that the unit square is in the quadrant 1, so theta goes from 0 to pi over 2. And so next, the trickier part is the boundary for r. Well, let's draw a line here. Not that line. Alright, so this line is, you see this line divides the unit square into two equal area triangles. And this line is theta equals pi over 4 radians, of course. So theta equals pi over 4 radians. And let's look at each of the triangles, the lower triangle and the upper triangle here. So in the lower triangle, which is theta from 0 to pi over 4, then let's draw a line r. And this length is 1. Well, this is the angle theta. And this length is 1 because it's unit square, and this length is tangent of theta. Alright, so for theta between 0 and pi over 4, which is basically in the lower triangle here, then r will go from, well, it will start from 0. It will start from the 0 here, and it will go to this whole length, which is the square root using the Pythagoras theorem, which is equal to the square root of 1 plus tangent squared theta. And 1 plus tangent squared theta is secant square, and secant square, and then the square root of secant square is secant theta. So r will go from 0 to secant theta. And that is for theta between 0 and pi over 4. And now for theta between pi over 4 and pi over 2, then let's do a similar thing. So, well, actually I don't need to erase that. Oh man, this is, well, so I messed up with the drawing. Oops. Alright, that should be good enough. Yeah, good enough. So for the upper triangle here, which is basically theta between pi over 4 and pi over 2, then, well, let's draw a line here, and then this is the angle theta, like theta is the angle starting from the positive x-axis. And then, well, this length is 1. This length is 1 because it's the unit square. And now this length is cotangent of theta. And so the r, of course, it will start from 0, and then it will go all the way up to this whole length, this whole line here. And so this will go from 0 to the square root of 1 plus cotangent square of theta, using the Pythagoras theorem. And so 1 plus cotangent square is cosecant square, and the square root of cosecant squared is cosecant of theta. So r will go from 0 to cosecant of theta for theta between pi over 4 and pi over 2. Alright, so that's how we get the boundaries for r and theta. And so you see here, r from 0 to secant theta for theta between 0 and pi over 4, and r goes from 0 to cosecant of theta for theta between pi over 4 and pi over 2. And using these boundaries for r and theta, we get, after interchanging the integral, not interchanging but changing the integral to polar coordinates, we get the integral I is equal to the integral from 0 to pi over 4 of, and then the integral from 0 to secant of theta r squared dr d theta. We integrate with respect to r first, because the boundary for r has theta in it. And then plus the integral from pi over 4 to pi over 2, integral from 0 to cosecant theta of r squared dr d theta again. We integrate with respect to r first. And so here we get, and so here you can see that for theta between pi 0 and pi over 4, r goes from 0 to secant theta. And for theta between pi over 4 and pi over 2, r goes from 0 to cosecant theta. And so integrating the r squared dr is easy. So after integrating that, we get, after integrating with respect to r, we get I is equal to 1/3 times the integral from 0 to pi over 4 of secant cubed theta d theta, plus 1/3 times the integral from pi over 4 to pi over 2 of cosecant cubed theta d theta. And so the next step is, so now we just need to solve these two single integrals, the single variable integrals, trig integrals. So now substituting theta to pi over 2 minus theta, we get the integral from pi over 4 to pi over 2 of cosecant cubed theta d theta is equal to the integral from 0 to pi over 4 of secant cubed theta d theta. And so the integral I is equal to, so 1/3 plus 1/3 is 2/3, so it's equal to 2/3 times the integral from 0 to pi over 4 of secant cubed theta d theta. Now we just need to solve for this integral, single variable trig integral. And so let's solve this by integration by parts. So it's the integral of u dv is equal to uv minus the integral of v du. And so secant cubed is secant times secant squared. So we'll choose u equals secant theta and dv equals secant squared theta. And so we get the integral from 0 to pi over 4 of secant cubed theta d theta is equal to secant theta secant theta times tangent of theta for theta from 0 to pi over 4 minus the integral from 0 to pi over 4 of secant theta tangent squared theta d theta. And so just plug in the values for theta from 0 to pi over 4, we get this is equal to square root of 2. And then tangent squared of theta is equal to secant squared of theta minus 1. And after expanding that out, we get this integral is equal to square root of 2 minus the integral from 0 to pi over 4 of secant cubed theta d theta plus the integral from 0 to pi over 4 of secant theta d theta. Now this integral should be easy to evaluate because that's just the integral of secant theta. You should know the integral of the trig functions. So that is equal to the natural log of 1 plus square root of 2. Now as you see, we have the integral from 0 to pi over 4 of secant cubed theta d theta on the left hand side, and minus the integral from 0 to pi over 4 of secant cubed theta d theta on the right hand side. So now we just add this to this side, so we get twice that integral is equal to, so twice that integral is equal to the square root of 2 plus natural log of 1 plus square root of 2. And so we just divide it by 2 to get the result for the integral. So the integral from 0 to pi over 4 of secant cubed theta d theta is equal to square root of 2 plus natural log of 1 plus square root of 2 over 2. So that's the result for the trig integral. And now we just substitute this result into this equation for the integral I for the original double integral that we are solving. So we just multiply 2/3 to it. And so our final result is the integral from 0 to 1 and integral from 0 to 1 of square root of x squared plus y squared dx dy is equal to square root of 2 plus natural log of 1 plus square root of 2 over 3. And so that is our final answer for the double integral. Thank you for watching.